The relativistic mass increase paradox touches on one of the strangest and most misunderstood ideas in Einstein's theory of special relativity. It asks, how can the mass of an object appear to increase simply because it moves faster? Isn't mass supposed to be a fixed, unchanging property? Let's begin with the basics. In everyday life, mass feels constant. A 1 kilogram object is 1 kilogram, whether it is sitting still or flying through the air. But when an object moves at speeds close to the speed of light, our classical intuition breaks down. Einstein's special relativity shows that as an object moves faster, it resists acceleration more strongly. To a physicist, this increasing resistance is explained as an increase in the object's relativistic mass. The faster the object moves, the more energy it carries, and since energy and mass are equivalent, E equals mc2, that energy shows up as additional mass. But here's the paradox, is the object really gaining mass? Or does it just act like it has more mass? The answer depends on how we define mass. Physicists now often avoid the term relativistic mass and instead stick with invariant mass, which is the mass an object has in its own rest frame when it's not moving. This is the same mass you'd weigh on a scale. It doesn't change no matter how fast the object moves relative to you. So what's actually increasing? It's the total energy and momentum of the object from the viewpoint of an outside observer. To accelerate the object further as it gets closer to light speed, you have to pump in more and more energy, but no matter how much energy you add, you can never reach the speed of light. The object appears to get heavier in terms of how difficult it is to make it go faster, even though its rest mass stays the same. Here's a question. Why can't we just keep pushing the object harder to reach light speed? Because the energy required grows toward infinity, the object's relativistic mass increases toward infinity, making further acceleration impossible. This is why no object with mass can reach the speed of light. Only massless particles like photons can travel at that speed. Let's take an example. Suppose you accelerate an electron in a particle accelerator. At rest, it has a small mass, about 9.11 x 10 minus 31 pkg. As you pump more energy into it, its speed increases, and so does its relativistic mass. In the lab, it behaves like it is much heavier, not because more matter is being added, but because energy contributes to how mass behaves at high speed. At extremely high energies, electrons can behave like they weigh hundreds or even thousands of times their rest mass. Does this mean that the object is gaining mass? It's more accurate to say it's gaining relativistic energy, and this energy behaves like mass, but its invariant mass, what a scale would measure if you could bring it to rest, remains unchanged. This paradox teaches us a key lesson. At high speeds, energy and mass blur into one another. What we think of as mass is just one way energy manifests. In fact, the whole idea of mass as a fixed property has to be re-examined when we enter the world of special relativity. One more thought, if you traveled alongside the fast-moving object, you wouldn't see its mass increase at all. It's only from the outside observer's frame that the object seems heavier. This tells us that mass and energy are not just properties of objects, they are also deeply tied to the observer's point of view. So the relativistic mass increase paradox isn't a contradiction, it's a sign that our everyday notions of motion and mass simply do not apply in the realm of high-speed physics. The paradox resolves itself when we understand that mass is not always as solid and fixed as it seems. Rest mass is an object's intrinsic property, remaining constant regardless of motion. Relativistic mass, historically used to describe increased resistance to acceleration, depends on an object's velocity. Modern physics replaces relativistic mass with energy and momentum to describe high-speed motion. This shift clarifies that mass itself does not increase, but the object's behavior in motion changes. A proton in a particle accelerator does not gain mass, but its energy increases significantly, like pushing a sled across ice. The sled doesn't get heavier, but resistance grows with speed. As an object accelerates, its total energy increases due to kinetic energy, making further acceleration more difficult. This increase in energy is often mistaken for an increase in mass, but in reality it affects the object's momentum. Modern equations express this relationship without changing mass, focusing instead on the transformation of energy. The faster an object moves, the more force is required to accelerate it further. In high-energy physics, particles need increasingly stronger electromagnetic fields to maintain acceleration, like rolling a snowball downhill. It doesn't get heavier, but it takes more effort to keep it under control. The closer an object moves to the speed of light, the more energy is required to increase its velocity. This follows from Einstein's equations, which show that infinite energy would be needed to push an object with mass to the speed of light. Since infinite energy is not possible, no material object can reach or exceed light speed. This serves as a natural speed limit, shaping the fundamental laws of the universe. Even with the most powerful particle accelerators, no proton has ever reached the speed of light. Like trying to reach absolute zero temperature, it requires infinite effort, but remains impossible. Newtonian mechanics suggests that applying force should always result in acceleration, but relativity modifies this rule at high velocities. As an object gains kinetic energy near light speed, its resistance to acceleration increases. This is because energy contributes more to momentum than velocity at these extreme conditions. The result is that further acceleration becomes increasingly ineffective. A spacecraft moving at 99% of light speed would require enormous amounts of fuel to gain just 1% more speed. Like pedaling a bicycle up a steep hill, the higher you go, the harder it is to keep climbing. The relativistic effects on mass, energy, and momentum are closely tied to time dilation. As an object moves faster, time slows down relative to an outside observer, altering how motion is experienced. This means high-speed travelers experience less time than stationary observers, further influencing measurements of motion and acceleration. Understanding this relationship is crucial in relativistic mechanics and space travel. Astronauts moving at high speeds in space experience time slightly slower than people on Earth, like watching a slow Meiji replay of a sports game. Time appears stretched depending on the viewer's perspective. Relativity shows that motion is not just about objects moving through space, but also how space and time interact. When an object moves faster, it follows a curved path in space-time, affecting its momentum and energy distribution. This curvature modifies the way forces act on the object, making acceleration less effective. The interplay of mass, energy, and space-time geometry is fundamental in explaining relativistic motion. The bending of light around massive objects, known as gravitational lensing, follows these space-time principles, like rolling a ball on a curved surface. The path is not straight but shaped by the environment. Particle accelerators confirm relativistic effects by accelerating subatomic particles close to light speed. The particles behave as predicted by relativity, requiring stronger forces to achieve smaller increases in speed. Their observed behavior aligns with the increase in energy and resistance to acceleration. These experiments validate Einstein's predictions and refine our understanding of matter and energy. The Large Hadron Collider pushes protons to 99.99999% of light speed, proving relativistic effects, like trying to reach the speed of sound. Once close, further acceleration requires exponentially more effort. If humans ever develop near-light speed travel, relativistic effects would drastically impact navigation and energy use. Spacecraft would require extraordinary energy efficiency to maintain acceleration without reaching impractical energy demands. Travelers at near-light speeds would experience time differently than those remaining on Earth. These principles shape realistic designs for future interstellar missions. A trip to a nearby star at relativistic speeds could seem like months for travelers but decades for Earth observers. Like watching a slow train from a distance. What seems fast to the passengers looks slower from afar. Modern physics avoids using relativistic mass because it is an outdated concept that causes confusion. Instead, energy and momentum describe how objects behave at high speeds without changing their fundamental mass. This shift refines the understanding of motion and interactions in extreme conditions. The focus on energy transformations instead of mass increase aligns better with experimental evidence. Modern textbooks teach that mass remains constant while energy accounts for relativistic changes, like redefining heat as molecular motion. It's a better way to describe the same phenomenon.